All right, we're talking polar coordinates and area here. So let's put our brains on this. In the past, if I had given you a circle, just kind of talk this through. So this would be a rectangular. Let's say I gave you this circle. And asked you to calculate the area from there to there. We would be calculating this area, correct? Between the curve and the x-axis in rectangular coordinates? Yes? Okay. Good. In polar coordinates, here's why polars are neat, because they give you a different way of measuring area. Come on. I draw the same circle. Or a sad attempt at it. We're actually, the area we are calculating here is here. Let's say we go from 0 to power 3. We were calculating a radial area now. Basically, you're looking at pi slices. So, if I were to draw any one of these, any one of those slices in there, basically looking at pi slices. So you're sweeping the area inside that curve, from the radius to the outer edge. From the origin to the outer edge, sweeping it through, instead of with rectangular between the x-axis. There's a difference there. You got to kind of switch your brain cells a little bit when you get the polars. It's a formula, okay? But you got to. The thing about this is you got to figure out what to add, what to subtract, if you have two shapes, etc. Okay. Does that give you a good idea? Good enough? Yeah. Okay, I heard a couple of uh-huhs, so I'm getting along. Here is the formula. What are the conditions? Remember this. It's continuous and it has to be fun. We are going from this is how your book notes it, from alpha to beta. So those are actually angles. So when I write out the formula, note that these are angles. You can also write it as such. But either of those will work. So we're basically applying a formula here. What we have, let's try compute the area of the right semicircle of R equals 4 times beta. You know what that looks like? Off the top of your head. It's okay if you don't. It's a circle, obviously, right? If you're given an equation, remember circles are, this is r squared, right? R. Sine theta, and then we move up and down on the y-axis. There's no cosine values here. This is all y values. So this is going to be placed at, what's pi over 2. 2 pi over 2 is the center. Okay, the radius is 2. So this is swept out. And here's the origin. Okay, I got to get myself in the board a little bit here. Pi over 2, 2 units up is the center. Right. This would be 4.
I see.
And pi over 2. So what we're asking for is the area of the right semicircle. So in here.
Oh.
So what are my bounds?
0, 2, 5, 2.
And 1/2 out, right? And then the rest of it is r squared. So 4 sine squared theta.
Do we really have to like memorize or use
You're gonna want to be pretty efficient at it. I thought you already had it memorized. So
right before the exam?
let's talk about cramming. It does not promote long-term learning. Thought you guys had learned your lesson by now. Okay. Again, there's an identity we need to use here, because sine squared is not an integral that we have in our pocketbooks, right? So we'll use this identity. So if I plug that in, I get 4 out front. And I have an integral now that I calculate that. Okay. Do you want me to run through the numbers on that integral, or you can handle it? Okay. The answer is in the book. Does that make sense?
So you take the half from the sine squared of 8. Right?
Yeah.
Okay.
Half times 8 is 4. And then 1 minus 2.
Okay, so you start off with 1/2 of the integral, and then 4 sine squared.
If this is 4 squared, 16.
16. Oh,
And
then
half
half
is
is
8.
16. Oh, okay.
Okay, geometrically, 1/2 pi r squared, right?
Yeah.
What's the radius? Pi r squared, and doesn't that give us 2 pi as well?
Yeah.
So, it's probably not gonna be this easy on the exam, obviously, but you can think sometimes in terms of just the shape. Geometric shape choice. Maybe, yeah, maybe. Okay, so let's look at a more difficult one. The area between two curves. Find the area of the region inside the circle r equals 2 cosine theta. And outside the circle r equals 1. R equals 1, right? And cosine theta. So we're looking for inside this and outside the other. Right? We're looking for the area here. What are their intersection points? What are those numbers? We're going to think through this the same way we would think through a regular rectangular coordinate problem. Find the intersections. Well,
Would you say?
2 cosine theta equals 1, right? So cosine's a half. Where does that happen?
I don't know.
One of those two. 5/3 is one of them.
Oh,
And that would be negative 5/3 or negative 5/3. We're going to go with negative 5/3 since we want to do this direction. Okay. If we went 5/3, we're going to see we're sweeping this whole circle here. We don't want any of this junk, do we? All we want is from here to here. Okay. So think. So if we have that, those are our intersections, right? So if we go from negative pi/3 to pi/3 for r equals 1, we are calculating this area, right? And if we go from negative pi/3 to pi/3 with 2 cosine theta, we're actually calculating this whole area in here. All right, so we have to do big minus this inside little to get the blue, right?
What about the edges around the outside of that? What edges? Like, into the green line, the red
Oh,
line?
here?
Yeah.
For the red circle, you gotta think in terms of, we're sweeping. Okay, so if I start at 0, I'm gonna sweep in this manner. Okay, right? If I start at, let's say, negative pi/3, I'm starting here and I'm sweeping Okay, so I'm actually leaving this blank. Makes sense? Yeah, so, yeah, it's a different way to think in those, in terms of those radial sweeping area
So you have to do
calculations.
the big one first, like you do like from -5/3 to pi/3 minus the inside, which is 0 to pi.
Right now, which is it?
This is what I
So for the big one, we want this whole area here, right? -pi/3, pi/3, of 2 cosine theta squared. Right? And then we want to subtract out this little one.
Okay, so then you do 0 to pi/3?
Nope. Pi/3, it's the same, for the same coordinates,
Oh,
because it's still -pi/3 to pi/3,
okay.
right? And then we have 1 squared. You're gonna have an identity to deal with here. Again. So that's 4, right? So we're gonna have a 2. Oh, that one's easy. What's cosine squared? They're usually given in your book. 1/2 1 plus cosine 2 theta. There's our identity. You want me to really go into that proof? Okay. Didn't think so. But after I look it up. You can finish the integral, yeah. But the hard part of these is just setting them up, because you've got to think in a little different terms than rectangular coordinates.
Do you have to do the identity, or you just do it out?
If this is a calculator-friendly problem, you can just plug it in.
Yeah.
Okay, right, so on the AP exam, this would probably be calculator-friendly, right? For now, in your book, if you're doing it by hand, you're given, this is given to you, right? It's in the margin of the book here.
Will they do like a cheat sheet with the sign or the trig identities?
So,
Too?
like I said, it'll be calculator-friendly if you need it.
Okay.
Yeah. Thanks, Logan.
Yep.
Okay. So I'm worried about the trig identities. I've never seen one where you needed it. And I've looked through a lot of years now, so, there you go. I mean, we could probably look through, let's do that. Just to kind of get your minds. Come on. There you go. BC. Let's just go. Okay. So let's look at some of the shapes they throw on the exam. Yeah. You're given the picture though. Okay, they give you the picture and say the graphs of the polar curves r equals 3, circle, and and 3 minus 2 sine 2 theta are shown from 0 to pi. They even give you it's 0 to pi. Okay. Let R be this region. Okay, the first one is find the area left. Okay. I'm not going to throw these at you yet. I just want to give you an idea what the picture we're going for.
How would you do that weird, like, where that intersection corner type is? How would you like do
This?
that? Yeah.
The beautiful thing about these is if you integrate 3 minus 2 sine 2 theta, you will take that into account.
Oh, for real?
Yeah,
That's good.
yeah, it's very cool. So you don't really have to worry about some of these funny losing shapes. You just have to be able to figure out which. And notice that was calculated friendly. So if you can set that interval up, you just bam, calculator. Okay, here's another one. Calculator friendly again. Okay. Look at that, it's a circle, r equals 3 this time, and r equals 4 minus 2 sine theta. So again, find the intersections, do your subtraction problem, put it in the calculator. What else is there? What's, okay, there's that. Okay, this is gonna be, you might not have one. Logistic equation, series. Okay, they didn't have one on this here. Whoa, it's very odd. Okay, this is 2012. They're pretty standard. Watch me be proven wrong again. Okay, here's the area question. It's actually parametrics. Is that right? No. No, that's just regular rectangular coordinates. They just put it in different terms. So you guys can do that one. Series, if you've probably seen that question. So like I said, about most of the time there is one on the exam, and most of the time it is a polar. Okay, here's one where they don't give you the picture. So, but they're not. I mean, it's calculator friendly. Use your calculator graph it. Okay, so you kind of get the idea. All right. Any questions? No? Good. I probably couldn't answer it. I'm pretty fresh on this stuff too. We will continue this section tomorrow with arc length and speed. Again, another couple formulas for you. And then Thursday, Friday, we move to vector value functions. What? You know anything about vectors?
Yes.
Okay, we're actually going to make functions with vectors. They're called vector value functions. They're really neat and really handy because you can do a lot of stuff with them. Slope fields, gradient fields. Yeah, I mean, you get 2 nights to do it. Do 1 per night. Practice. Okay. It's all about practice, man.
You're not 5, practice.
Holy cow.
Ramon, what'd you give me?
You gave me a lot of
Holy
crap.
crap.
That was you.